So far we discussed about different aspects of microstructure. What are the shapes of grains and what is the different defects in the microstructure of the or the arrangement of crystals in a crystallographic material. Okay, so for all these things, to identify the defects or to actually finding the shape of the grains or size of the grain, for all these things we need to see the microstructure of the material. Okay, we need to see the microstructure of the material. So to see this or to view this microstructure of the material, we use this technique, microstructure determination. Okay, so by this microstructure determination, we can see this microstructure of any material using a using some equipments. Okay, and by this microstructure determination, we can reveal the structure of grains, what is the size of the grain, what is the shape of the grain, and what are the grain boundaries, what is the characteristics of this grain boundary, and what are the different defects present in the microstructure of the material. All these things can be revealed from by viewing this microstructure of the material. And of course, based on this uh, component, after viewing these microstructure components, we can find the behavior of the material from that parameters. Okay, for example, we can see the grains. Grains are columnar grains or fine grains or coarse grain or equiaxial grain. So by seeing that, we can actually identify the shape of the grain. Thereby, we can study the behavior of the material also. Okay, and the first stage of this microstructure determination is specimen preparation. Okay, first stage is specimen preparation. So during this specimen, these are the stages of this preparation or viewing this or microstructure. These are the stages. First, we cut the specimen from the parent metal. Okay, we select the parent metal, then we cut the specimen from the parent metal. And after the cutting, the second stage is rough grinding to remove all the different imperfections in the surface. Okay, for that we remove the all the imperfections in the surface using rough grinding. Then we next one is intermediate and fine grinding. So after fine grinding and polishing, we got a smooth surface. Okay, that will reveal the microstructure of the material. And finally, to see the grain boundaries and all the grains, we use an etching. That is a chemical process. Okay, so these are the stages of different surface preparation for this microstructure study. Okay, so first stage is selection and cutting of specimen. So, for example, after any manufacturing process, for example, after casting or after forging, we have a parent metal, and from the parent metal, we cut the specimen for the determination of this microstructure. And that specimen should be a true representative of material being studied. For example, in case of casting process, there may be some segregation of the components inside the casting process. Okay, during casting process, while melting, so in this container, I am cast the product. So while melting, so this is the base metal or pure material, but these are the impurities or alloy elements, for example. Okay, so there is a chance for high concentration of alloy elements in the bottom region. Here we can see in the bottom region we have high concentration of alloy elements. So if we cut a particular section from here, the sample microstructure will be different from this segment, because here in this segment the microstructure contain more number of alloy elements or impurity than that of this structure. So we have to cut a particular section which will be the true representative of the base metal. Okay, it should be the true representative of the base metal. So we have to select such a segment from the base metal. And another one is the base specimen should be free from the region of specific interest. Okay, should be free from any, for example, similar to this case. In the bottom region, it is contained with the more amount of alloy elements. So we have to select a region with the specific interest. Okay, if you want to study that segregation process, we have to select that area. And we use an abrasive wheel or a saw for cutting the specimen from the parent metal. And during that process, it should ensure that no heating will occur during the cutting process. Should not be any heating during the cutting process. What happens if the specimen is heated during cutting? If it is heated above recrystallization temperature of the material, entire grain structure may alter. Maybe before heating or before cutting, the grain structure may be a fine grain structure. But during cutting process, if any heat is developed across a cross section, that may lead to change the grain structure, or grain size may change, or grain shape may change. So it should ensure during cutting process, no heat should be developed across the specimen. And for that, we can use different cooling arrangement. We can provide some water cooling, or some coolant can be used to cool the material during cutting process. Thereby, we can avoid this heating of the specimen during cutting process. And we take 15 to 10 mm to 15 mm size diameter square specimen for testing. Okay, it's a very small testing space. Very small testing piece, 10 mm to 15 mm size only for the specimen. Okay, and this is not actually not a standard size. We can take any size, and we can take any shape for the specimen. Okay, and it's dependent upon the process which is used. And we cut the specimen, and commonly we use 10 to 50 mm diameter, or circular specimen, or a square specimen is commonly used for as a specimen. Okay, and if we use a very small specimen, for example, in some case we have to use very small specimen, very small specimen. So in that case, we use a mounting technique. Mounting technique. So by using mounting technique, what is advantage? For example, maybe the specimen may be irregular shape, or the specimen may be very small in size. So in that case, further processing will be very difficult. We have to polish, we have to grind this specimen. So in all this process, it will be very difficult if the specimen is very small, or specimen is very irregular in shape. So what we do, we mount some thermoplastic resin around this specimen. So we can increase the size of the specimen by adding thermoplastic resins around this specimen. So that is called mounting process. So we will, I will show a video how this mounting is. Mounting process of the specimen. So this is the mounting process. So this is the chemical or powder which is used for mounting. Okay, there are two chemicals are used. So this is another called setting chemical, a liquid. So both are mixed together, and so this is our specimen. This is our specimen, and this is the mold which is used for mounting. Okay, and inside this mold, and we use some grease. This grease is applied around this mold, and this is for easy removal of the material after molding. We apply grease around this mold, and after that, this is the compound preparation for the thermosetting plastic. Plastic can be used as a molding material, and after proper stirring, we kept the specimen inside the mold. We can see the specimen is, this one is specimen, and specimen is kept inside this mold. Okay. Then we pour the chemical inside the mold. We pour the chemical inside the mold. Okay. Then we allowed to solidify this mold. Then after that, after this preparation, and we got this product. See this, the center region is the mold, and all the outer region is actually thermosetting plastic. Okay, so this thermosetting plastic actually bind this specimen with this plastic. So if the specimen is very small or irregular in shape, by this mounting technique, we can increase the size of the specimen. So we can easily hold this specimen during the further process. For example, for grinding or for a polishing process, etc. We can very easily hold this specimen. If it is a very small specimen, it is very difficult to hold that specimen for further process. So we increase the size of the specimen by adding some thermosetting plastic around this specimen. Okay, actually we use this area for determine the microstructure. So this area is not covered with this mounting material. Okay, actually we cover the mounting material with the other surface areas. So this area is actually exposed. This is the specimen area, and this area actually used to determine the microstructure. Okay, so this is the mounting technique used for specimen preparation, and for that we can use different machine also. So this is the structure after mounting. Also, this we can see this white color. This is a specimen. So this specimen is very difficult to process. So we attach this specimen with the other material, so that in the entire system can be used for further process. And after that mounting process, the next process is rough grinding and fine grinding. And here we use emery paper for grinding process using emery paper. So this is the emery paper. You may see this emery paper for wood polishing. Okay, so emery paper has different size. So grit size. So for rough grinding, we use grit size of 80, 100, etc. So by increasing the grit size, the polishing become more finer. Okay, so here in the rough grinding, we use emery papers with the grit size around 80, 100, 120, etc. Okay, and by this grinding, rough grinding, we remove all the coarse filing abrasive particles. Sorry, we remove all imperfect. We can create a flat surface by this rough grinding. After that, we remove all the abrasive particles by washing with the water. Okay, so first one is the rough grinding process. Here we can see this one is the rough grinding. This is a machine used for grinding. So this is the emery paper, and we hold the specimen against the emery paper, and the emery paper is actually running using a belt. Okay, and by this method, by friction between the emery paper and the specimen, we got a flat surface. After, see this, a flat surface is the, we got flat surface. After that, next one is the fine grinding, where we use different emery papers, 180, 240, etc. Of the size of the, we use different emery paper, and which is in the increasing order of the grit size. So see this, okay, which is arranged in a sequence in the increasing order of the grit size. And first we polish in the or grind in this emery paper with the lower grit size. Then we polish on the or grind on the higher grit size emery paper. So this is the polishing, grinding process, fine grinding process. So all the scratches which is in the which is formed on this coarse grinding is removed or removed by this process. Okay, so this is a grit size increasing order 220, the first grit emery paper, then 320, 400, 600, etc. Okay, that is intermediate grinding. Then after that, fine grinding 1/0, 2/0 grit mini papers are used. So here we can use either machine or by manually we can grind using we can grind that. Okay, so by after fine grinding we got a mirror finish, a shining and a scratch-free surfaces got after this fine grinding, and after grinding we wash the specimen with the water. Okay, that is the fine grinding. After fine grinding, next process is polishing process. So this is the grinding process. We use different membrane paper for fine grinding, and then after that we wash the specimen. Then we hot using any hot stream. We just remove all the water content from the specimen, and this is the polishing machine. It's a polishing machine. Okay, in this polishing machine, where we use a some rotating cloth part. Okay, we use a rotating cloth part impregnated with some polishing medium. Okay, so in that machine we can see a rotating cloth part, and by polishing we can remove all the varnish, all the glues which is available in this fine grained material. Okay, small grooves are present and which can be removed by this polishing process. And in this polishing process, we use a rotating cloth with the polishing medium. Okay, and here we held the specimen against the rotating cloth with the sufficient pressure. Okay, we can see that. So this is this red one is the rotating cloth. Okay, and in that rotating cloth, we will provide some material. This is aluminum. Aluminum. So we see this aluminum is, we put some aluminum into this rotating cloth, and this is first stage of, and we apply some amount of water. Then we hold this workpiece specimen against this rotating cloth so that polishing will occur. Okay. So this is the first stage of polishing. After first stage of polishing, this is the second stage using diamond. Okay, so this is the diamond paste is used here in this polishing. So this is diamond polish is applied in the rotating cloth. Then again we hold the specimen against the rotating cloth. Okay. And after that, we wash the specimen, and we can see a mirror finish in the material. A mirror finish. Okay. The mirror finish surface is produced after polishing. So that is the polishing process. There are two types of polishing: alumina polishing. Polishing medium is aluminum paste, and the second one is diamond paste. Okay. And after that, so we got a mirror finish surface of the specimen after polishing. Then we, to reveal all the concern, that means a grain boundary or grains, all this, to reveal all these things, we use some chemical treatment also. Okay, so after getting this mirror finished surface, the microstructure is revealed by a chemical surface treatment using some appropriate chemical agent. Okay, that process is called etching process. So we apply some chemical reagent and we reveal all the microstructure from the smooth mirror finish surface. And there will be a chemical reaction, and the chemical reactivity of the grain depend upon the crystallographic orientation. Since the atoms in the grain boundary is more chemically active, they dissolve at a greater rate than that of within the grain. So we already studied within the grain. If we consider two grains, this is the grain boundary region. In this grain boundary, the atoms are misoriented, are not strongly bonded with the adjacent atom. So we can say the energy of the atoms in the grain boundary is very high. They are chemically active. So when some chemically reactive agents, when in come contact with these atoms, what happens? They will react with this atom. So the atoms which is in the grain boundary region first react are more chemically active to the external agents than that of the atoms in this interior portion of the grains, because the interior portion of the grains are perfectly bonded. Okay, so this is not chemically active, but the atoms in the grain boundary region is chemically active. They will react with the external chemical agents. Okay, so this grain boundary region react with the chemical agents. Okay. So since the atoms along the grain boundary region are more chemically active, they dissolve at a greater rate than that of the within the interior grain. So HNs are chosen depending upon the material composition. Depending upon the material, there are different HNs are available. This is a chemical material. And HN is used to dissolve this layer and remove it. And cleaning before etching and drying, we use water cleaning, and dip and agitate the specimen in the etching reagent for a few seconds for chemical reaction. Then after, we quickly wash with the running water. So that is the process of etching. So here we can see the etching process. For the etching process, we use nitral. 2% nitral is a etching agent. And nitral is another etching agent. Potassium dichromate. So we take a cotton and we apply this reagent into the surface, and after applying, we kept that specimen on a running water. Okay. So we can see after applying etching process, we can see that surface become darkened. Initially, after polishing, it was a mirror finish surface, but after etching process, we can see the surface become darker. So this depend upon the darkness of the surface is depend upon the depth of etching. Okay, if we supply more chemically reactive reagent, then the depth will be high. The surface become more darker. Okay. So based on the color, actually we determine the depth of the etching process. And we remove all the impurities from the surface using any chemical, and the surface become dry. And after that, we remove all the water particles. Okay. So this specimen, this surface is ready for microstructure analysis using any microscope. Okay, so that is the etching process. So then these are the different types of etchants used, and the etching time specified, and its composition is given. And these are the different materials. For the, you can see for high carbon steel, we use picral etchant. Okay, so for depending upon the material, we have to change the etchant. So thereby we can prepare the surface for this microstructure analysis. And after that, we can use different microscope. Optical microscope can be used, where 1000 times magnification is possible in optical microscope. Then after that, or we can use electron microscope for that. Then TEM, transmission electron microscope, can be used, or we can use scanning electron microscope. Okay, so these are the different microscope used for study the specimen. After this specimen preparation, we kept the specimen inside the under this microscope, and we can see the microstructure using this microscope. So this is your assignment. The different types of microscopes used for determination of microstructure. So you have to study these different types of microscope, and you have to prepare an assignment based on that. And I will give the assignment topic in the classroom. Okay, so this is your assignment. I'm not going to explain this microscope. Okay, any doubt about surface preparation? Okay, now. Okay. Move ചെയ്യാം. കേൾക്കണല്ലേ നിങ്ങള്? ഓക്കെ അല്ലേ?
Okay, sir.
Okay. So after surface preparation, we can study the microstructure using different microscope. Okay. ഒരു small topic on finish ചെയ്യാം. Okay. So next one is X Ray Diffraction. This is another technique for microstructure study, determination of microstructure using X Ray diffraction. Okay. So you may heard about X-rays. So X-ray actually that is discovered accidentally in 1895 by Wilhelm Röntgen in 1895. That is actually the discovery of X-ray waves are accidentally, and that is a wave nature, wave nature ray. Okay, the rays have maybe a particle nature or wave nature, but X-ray is a wave nature ray. Okay, and this X-ray can be used for determination of microstructure. Okay, it can be used for determination of microstructure, and based on the experiment of Friedrich and Nipping. Friedrich and Nipping are the two scientists. They are conducted a experiment in 1912, and based on this experiment, he observed that when X-ray passing through a specimen, they observed some regular spots on the X-ray paper. Regular spots on the X-ray paper. Okay, they observed. And based on this regular spot, they concluded that the X-rays are waves. X-rays are wave type nature. They have wave type nature. Okay, so sorry. So this is the regular arrangement of in the X-ray paper, and based on this regular arrangement, they concluded that the Friedrich and Nipping concluded that this regular arrangement because of the regular arrangement of atoms. Regular arrangement of atoms. Okay, and actually from this experiment, the metallurgists concluded that in a crystal, the atoms are regularly arranged. So this is the first observation. Okay, this was the first observation or first conclusion that all the atoms are regularly arranged in a crystal. Okay, and one more conclusion from this experiment, that is the X-rays are wave nature. Okay, so these are the two conclusions. First one, X-rays has wave nature. That is the first conclusion. And second one is that crystal has periodic arrangement of atom or regular arrangement of atom. So based on this, they got Fedris and nipping. This is a very important experiment, and the result from the experiment is very, very important for metallurgy and material science. Okay. So this X-ray diffraction of an experimental tool to explore the internal structure of the crystal. Okay. We can use this X-ray diffraction technique as a tool for the internal microstructure determination, how the atoms are arranged inside the material. Okay, so this is the X-ray diffraction technique for the microstructure determination. So when an X-ray beam, that is a wave nature beam, when it is incident on a sample material, what happened to that material? Sorry, what happened to that beam? Some amount of beam will transmit. Okay, which will transmit through the specimen. Like when the light passing through the glass, what happened? It is transmitted through the glass. Similarly, some amount of incident beam is transmitted through the glass, and some amount of incident beam is scattered with the particles inside the sample, and that scattered beam is the diffracted beam. Okay, that scattered beam is the diffracted beam. So during scattering, two things will happen. One is these two beams, when two beams scattered, they may constructively interfere. They may constructively interfere. So when the beams are scattered from the sample, the two beam, if you take two beam, there are two chances for interference of this beam. First one is constructively they may interfere. Second one, they may destructively interfere. Okay, what is constructive interfere? For example, these are the two X-ray beam, the X-ray beam wave 1 and wave 2. Here we can see the amplitude is same, the frequency is same, okay, the phase is same for these two beam. After when it is strike on the specimen, so this is a scattering event. That means when it is strike on the specimen, what happened? Here again wave 1 dash is formed and wave 2 dash is formed with the same amplitude. But when they come in contact, when they two waves, when they interfere constructively, this is the resultant wave. When these two waves after scattering, when they interfere constructively, this is the resultant wave. What happened to the resultant wave? They interfere and the amplitude of the wave, resultant wave, is increased by 2a. And there is no change in the phase and frequency. But here we can see the amplitude is increased by 2a. Initially it was both has a and a amplitude, but it's increased to 2a. So this is a constructive interference. Constructive interference. Okay. So the wavelength is, there is no change in the wavelength. Wavelength is lambda. And what is for this one? For this one, here we can see initially this is the X-ray wave, incident X-ray beam. So both has wave 1 and wave 2 has same wavelength, amplitude, frequency, phase. But after scattering, we can see wave 1 dash. After scattering, wave 1 changes to wave 1 dash. What happened to that? There is no change. The amplitude is same, phase is same, frequency is same. Okay. Sorry, destructive interference. After scattering, what happened? The amplitude is same, the wave 3. Amplitude is same, frequency is same, phase is also same. But for wave 4, after scattering, we can see its phase is changed. Initially, we can see this peak region here, but here the peak region is reversed here. Here the peak region is here below the center line, but here peak region is above the center line. So the entire phase is changed after scattering. So when the incident beam scattered when with a particle, the incident beam exactly its phase is reversed. But here for this wave, there is no change. Wave 3, There is no change in the phase and amplitude, etc. But here the phase is changed. When these two being combined, the resultant beam will be a completely destruction. That means there is no wave. When they combine together, it will be a removal or complete disappear of this beam. Complete disappear of this beam. When they combine, this is called destructive interference. So after scattering, these two events may occur. First one is constructively interfere. That results into stronger beam. A stronger beam with a two-way amplitude by constructively interfere of two beams. Another one is after scattering, the two beam may destructively interfere, resulting in the disappearance of the beam. These are the two events that may occur when the incident beam scattered with the particles inside the sample. Okay, so actually in X-ray diffraction for determination of crystal structure, we are not using this transmitted beam. Okay, we are not using this transmitted beam. We use this transmitted beam for reveal the structure of bonds. Hospital to reveal the structure of our bonds. Fracture what we do? X-ray use it. Upper use in transmitted beams. When the incident beam passing through the bond and tissues, we got an image of the bond using this transmitted beam. This transmitted beam, when it is passing through the X-ray paper, we got the structure of our bond. Fracture check. So after the transmitted beam are using it. But here for determination of crystal structure, we are using this diffracted beam or scattered beam. We are not using this scattered and transmitted beam. Okay, so this scattered beam can occur constructive interference or destructive interference. Okay, no doubt? Any doubt? Any doubt about this constructive interference and this destructive interference?
No, sir.
Okay. So this diffraction is occur. Diffraction phenomenon is occur by this constructive interference or destructive interference. So diffraction is a consequence of specific phase relationship established between two or more waves. Then they have been scattered by the obstruction. Diffraction occurs when the wave encounter a series of regularly spaced obstructions that are capable of scattering the wave and have the spacing comparable in magnitude and wavelength. So this diffraction is occurred due to this phase difference. Here we can see the phase difference is opposite, reverse. So that is the disappearance of the wave, that is called destructive interference, and a diffraction is occurred. And here the constructive interference because of the same phase, and a large magnitude wave is produced. Okay, so this is the diffraction. By scattering of the beam, a diffraction is occurred. When you come to the microstructure, what happened to this beam? So this is the incident beam. So inside the sample, this is the arrangement of atoms or particles inside the inside the sample. Okay, so this is the incident beam. What happened to this incident beam? When it is incident on this particle, I am taking only this particle. Okay, actually this beam is incident on all particle, but I am taking only this single particle. When the beam, X-ray beam ray incident on this particle, what happened? Two things will happen. One is transmission, similar to this case. A beam is transmitted. Other one is scattering of all beam with this particle. So these two events will occur, scattering as well as transmission. Okay, and this is for a single particle, but the beam, when the beam strike on all the particle, this scattering as well as this transmission occur on all particle. Okay, scattering as well as this transmission occur on all particle. And in this scattering, here we can see different direction in the scattering. Different direction. around the particle, there are different directions for the scattering. But when we check this direction, if we check this direction of all scattered beams, this beams is constructively interfere. These beams in this direction is constructively interfere, because in this direction, for example, this is an example. In this direction, the rays has same phase. In this direction, the ray has same phase. That means the rays has same phase, means they are constructively interfere. What is the resultant? The result is a strong beam, strong ray with a double amplitude. Okay, when the two waves are constructively interfere, the amplitude is doubled. When 10 waves are constructively interfere, the amplitude is 10 times. So, for example, here in this case, in this direction, the waves are same phase. We assume that here in this direction, the waves are same phase. What happened? All the waves are constructively interfere, and which result into a stronger beam or stronger wave in this direction. A stronger wave is produced in this direction. Okay, by the constructive interference. But maybe for another direction, for example, in this direction, I am taking another direction. Sorry, I will take another direction. Okay, for example, this direction. In this direction, maybe the this is not in the same phase. The atoms or the scattered beam is not in the same phase, so there is no chance for constructive interference. But in the red direction or this blue direction, in this direction, all the scattered beams are in the same phase. That leads into a high, stronger wave, scattered wave in that direction. Okay, so we got a stronger wave in that direction. A stronger wave. That is the resultant of constructive interference of all the scattered wave in the direction which is in the same phase. Okay, so we got a scattered wave. And if you take another, one, okay, that is okay. So we got a stronger wave in this direction. So this wave is the diffracted wave, a diffracted wave by a constructive interference. Similarly, in this direction also, the scattered waves are added together or constructively interfere, form a diffracted wave. So such a way, the incident wave beam converted into a diffracted beam. Okay, by the constructive interference. And maybe in another direction, the beams may be destructively interfere and disappear. There is no resultant wave after destructive interference. Okay, so when the path length of the difference in the integral number of wavelengths, scatter waves are still in phase. Wavelength same phase anengil, they are said to be mutually reinforced or constructively interfere with another, and amplitude are added to them. Diffracted beam is one composed of large number of scattered waves. They are mutually constructively interfere with one another. So by this way, we got a diffracted beam. Okay. So similarly here, all the scattered beams in the blue color, with the blue color is in the same phase, constructively interfere, which are resulting in a higher magnitude diffracted beam. High amplitude or reinforced amplitude diffractive beam. Okay. And here we can see this diffraction. So here a black color incident beam, a blue color diffracted beam. So this is the diffracted beam. This one is the diffracted beam. Actually, which is incident beam is striking on the particle, and which is diffracted away from the particle. Okay, that's the basic concept. Actually, എന്താ സംഭവിക്കുക? ഈ എക്സ്റേസ് ഇവിടെ സ്ട്രൈക്ക് ചെയ്യും, ഡിഫ്രാക്ട് ചെയ്തു പോകും. സെയിം ഫേസ് ആണ്, ഇതുപോലെ ഡിഫ്രാക്ട് ചെയ്തു. ഇതാണ് ശരിക്കും സംഭവിക്കുന്നത്. ബട്ട് ബ്രാക്സ് എന്ന് പറയുന്ന സയന്റിസ്റ്റ് ഒരു എന്താ പറയാ, ഒരു കൺക്ലൂഷനിലെത്തി. എന്താ, ഈ പാർട്ടിക്കിളിൽ നിന്ന് ഡിഫ്രാക്ട് ചെയ്യുന്നതിന് പകരം അദ്ദേഹം പറഞ്ഞു, പാർട്ടിക്കിളിൽ നിന്ന് ഡിഫ്രാക്ട് ചെയ്യുന്നതിന് പകരം വി ക്യാൻ കൺസിഡർ ദാറ്റ് ആസ് എ the diffracted with this plane. We can draw a plane which is connecting these particles, or slip planes ആയിട്ട് കൺസിഡർ ചെയ്യാം. സ്ലിപ്പ് പ്ലെയിൻ വേണ്ട, we can consider a lattice plane. ഒരു മില്ലർ ഇൻഡിസസ് വെച്ച് അതിനെ അഡ്രസ് ചെയ്യാം. So actually this is diffracted, this incident beam is diffracted by this particle. പക്ഷെ ബ്രാക്സ് എന്ന് പറയുന്ന സയന്റിസ്റ്റ് അതിനെ മറ്റൊരു രീതിയിൽ ഇന്റർപ്രറ്റ് ചെയ്തു. Instead of diffracting in a particle, actually this wave X-ray diffracted with respect to this plane. Okay, so here we can see a horizontal planes incident beamsonu adu diffract cheyidu or particular direction. Okay, appo here ivide this diffraction, by this diffraction, this angle, if you take this angle theta, the angle between incident beam and this plane, that is equal to theta. This will be also equal to theta. The diffracted beam and the diffracted beam and this plane also make an angle theta. Okay, so we can say this diffraction as a reflection also, because here this angle is same. Okay, incident beam and a plane make an angle theta. Diffracted beam and this plane make an angle, same angle theta. So this theta and this theta are same. We can say this is a reflection. What is reflection? ഒരു മിററിലോ ലൈറ്റ് അടിച്ചു കഴിഞ്ഞാൽ റിഫ്ലക്ട് ചെയ്യും by a same angle. So that is reflection. So friend, this Bragg's develop a law. So this is the first law of Bragg's law. First part of Bragg's law. Okay, so Bragg concluded that the diffraction can be considered as a reflection. Okay, this diffraction can be considered as a deflection. Engane consider that these two angles are same. This angle and this angle are same. So we can consider as a reflection. So this is the first part of Bragg's law. For every diffracted beam, there exists a set of crystal lattice plane. So this is a crystal lattice plane. So he assumed a crystal lattice plane such that the diffracted beam appears to be specularly reflected. Completely reflected means specularly reflected from this set of planes. So diffracted beam actually a reflected beam. That is the first Bragg's law. Okay. So this is the Bragg's law, first part. The diffracted beam appears to be. It's not actually a reflection. Actually a reflection, but that is appears to be a specularly reflected from a set of crystal lattice plane. This is the plane. So this is the incident beam, make an angle theta. This is the diffracted beam that can be appears as a reflected beam. And here the angle of incident and what is the reason for this specularly reflected beam? This is the reason. The angular incident and angular reflection is same. Both are same. So incident beam and reflected beam are normal, and of course both are in the same plane also. Both are in this plane of sheet, plane of screen. രണ്ടും സെയിം പ്ലെയിനിലാണ് ഇൻസിഡന്റ് ചെയ്യുന്നതും റിഫ്ലക്ട് ചെയ്യുന്നതും. ഈ പ്ലെയിനല്ല ഉദ്ദേശിച്ച് ഇൻസിഡന്റ് ചെയ്യുന്ന പ്ലെയിനും, അതായത് ഈ യെല്ലോ കളർ, ദാറ്റ് ഈസ് എ പ്ലെയിൻ, യെല്ലോ കളർ ഷീറ്റ് ഈസ് എ പ്ലെയിൻ, അതിലാണ് ഇൻസിഡന്റ് ചെയ്യുന്നത്, റിഫ്ലക്ട് ചെയ്യുന്നത്. അപ്പൊ അതുകൊണ്ട് തന്നെ we can consider this as a specular reflection. So that is the first Bragg's law. The diffracted beam can be considered as a reflected beam. Okay. So ഇങ്ങനെ ഒരു beam വന്ന് ഇതുപോലെ diffract ചെയ്തു. Similarly, we consider another beam. Another beam. So this is the direction of beam, the red color. This red color is another direction of beam. And finally, the resultant after constructive indifference, this is the resultant beam with a very high amplitude. And here in this, we can draw a plane which is in this direction. This is the direction of plane. So here also we can develop a plane, and where he can say the angle between these two are theta. Here, if you construct a plane here, this angle and this angle between the plane and this red resultant constructive interference beam and incident beam will be same. Both are theta. Okay, so in this way we construct a plane. Okay, so this is the set of planes in the lattice. Okay, so that is the Braggs law. So there exists a set of crystal lattice plane. So നമ്മൾ അവിടെ അങ്ങനെ ഒരു പ്ലെയിൻസ് കൺസ്ട്രക്ട് ചെയ്യാണ് ഇത്. അപ്പൊ ആ പ്ലെയിൻ കൺസ്ട്രക്ട് ചെയ്യുമ്പോഴുള്ള കണ്ടീഷൻ ഇതാണ്, ഈ തീറ്റ ആംഗിൾസ് സെയിം ആവുന്ന രീതിയിൽ വേണം ഈ പ്ലെയിൻ കൺസ്ട്രക്ട് ചെയ്യാൻ. Okay, and from this we can develop a law that is the second part of Braggs law. This is the actually the first part, and the mathematical expression of this first part of Braggs law is the second part. This is the second part. This is the mathematical explanation. So here from this we can say, what is this distance? This distance is equal to interatomic distance. That means the distance between the one plane and the next plane. That is the interatomic distance. The distance between the two atomic arrangement. This distance. That is the interatomic distance. That is in the x scale. S and the remaining things is Miller indices. D scale. Scale is the Miller indices of that plane and that planes. Okay, two parallel planes. So this is the interatomic distance between the two atoms. And from this he developed this equation: 2D scale sin theta is equal to n lambda. N lambda is equal to 2D scale sin theta. And this is derived from this figure. Here we can see one beam is incident here, and this is diffracted. Another beam is incident in this another atom. Here we have an atom. Here we have another atom, and this is the interatomic distance. This is the two planes, lattice plane for the diffraction or reflection. Okay, and here in this we can construct two right angles. This angle is theta, this angle is theta, then this will be theta, and this distance is a scale. So by applying the Pythagoras theorem for this rectangle, what is sin theta? Sin theta is equal to QR by S scale. QR by S scale. That is the sin theta. And okay, we got QR by D scale equal to sin theta. So QR equal to sin theta into D scale. Similarly, what is PQ? PQ equal to, again, similarly considering this right angle. We got PQ equal to D scale into again sin theta. Okay, so QR equal to from this we got QR equal to D sin theta. So by adding these two, we got QR plus PQ equal to 2D sin theta. Okay, QR plus PQ is equal to 2D sin theta. So from this, what is PQ and QR? That is the path difference. This is the extra portion of beams. Itra extra portion of beam compared to this beam. This beam in compare cheyumbo idana extra amount of beam. Baki idu noki ee length rendu same alle. Ee region ulla ee length same ah. Adone ee region ulla ee length same ah. So this is the extra portion PQ and QR. And this extra portion is equal to N lambda. We can consider PQ and QR as N lambda. That is N times of the wavelength. From this we got N lambda is equal to 2D sin theta. That is the second part of the Bragg's law. Okay. And based on this, these Bragg's got a Nobel Prize. And it's a very simple experiment. But he got a Nobel Prize, and it's a very important experiment on the conclusion from this experiment. And just he called diffraction as a deflection. That is the conclusion. From this, his experiment, he just concluded that this diffraction is equal to deflection. And from this, he developed this equation, N lambda is equal to 2D sin theta. So that is the X-ray diffraction. Based on this, we can determine the interatomic distance, and we can study the microstructure of the or crystal arrangement of the material. Okay, Bragg's law. N lambda is equal to 2D sin theta. N may be any integer, 1, 2, 3, etc. Lambda is the wavelength, D is the interatomic distance, theta is the angle of incidence. So from this, we can calculate the D is equal to A divided by, we already studied this in the Miller indices. HKL are the Miller indices. HKL are the Miller indices. A is the cube, A is the size of the cube, or the dimension of the edge of the cube, A. Okay, this is A, this edge. And H scale is the Miller indices. From that also we can calculate the interplanar spacing or interatomic distance. Okay. And this is the diffractometer, which is used to study the microstructure of the material. So here we use a specimen, and we use a source. From the source, a ray is incident on the specimen, which is strike on the particles, atomic particles, then they get diffracted. Okay, and we place a paper, X-ray paper here in this region. We are not providing X-ray paper here. We will not provide any X-ray paper or place X-ray paper here, because this is the direction of transmitted beam. Okay, transmitted beam. We are not considering that. We only place the X-ray paper here, and we, based on the diffraction, some spot will be created in the X-ray paper. So this is diffractometer. So apparatus used to determine the angle at which the diffraction occurs. Counter is now is mounted on the mobile carriage that is obtained angular position. This is called counter. This region is called counter. Collimator are compared with the beam path to produce a well-defined forced beam. But a collimator and other base use filters use monochromatic adler beams produce. So this is the setup. X-ray diffraction setup. Okay, and this is the output from the experiment. Diffraction from the diffractometer. You can see the peaks, and from the peak, which is actually different planes. Each peaks indicating different planes. Okay. Application, we can determine the crystal structure, grain size, phase, phase fraction. ഇതെല്ലാം determine ചെയ്യാനായിട്ട് നമുക്ക് എക്സ്റേ ഡിഫ്രാക്ഷൻ യൂസ് ചെയ്യാം. ഇനി ഇത് വെച്ച് നിങ്ങൾക്ക് പ്രോബ്ലംസ് ചോദിക്കാം. ആ പ്രോബ്ലംസിൽ നിങ്ങൾ ഈ ഫോർമുലാസ് ആണ് യൂസ് ചെയ്യേണ്ടത്. മില്ലർ ഇൻഡിസസിന്റെ സ്കെയിൽ വാല്യൂസ് തരും, അതുപോലെ എ വാല്യൂ തരും. ഫ്രം ദിസ് യു ക്യാൻ ഫൈൻഡ് ദ ഇന്റർപ്ലാനാർ ഡിസ്റ്റൻസ്. ഓക്കെ, യൂസിങ് ദിസ് ഇക്വേഷൻ. ഇതുപോലുള്ള പ്രോബ്ലംസ് നിങ്ങൾ ചോദിക്കാം. അതുപോലെ തന്നെ തീറ്റ വാല്യൂസ് വരും. തീറ്റ വാല്യൂസ് കാൽക്കുലേറ്റ് ചെയ്യാൻ പറ്റും. എൻ ലാംഡ ഈസ് ഈക്വൽ ടു 2d sin തീറ്റ വെച്ചിട്ട്. ഓക്കെ, ഇതുപോലുള്ള പ്രോബ്ലംസ് ചോദിക്കാം. അത് ടെക്സ്റ്റ് നോക്കി പ്രോബ്ലംസ് കാൽക്കുലേറ്റ് ചെയ്തോളൂ കേട്ടോ, പഠിച്ചോളൂ. ദാറ്റ് ഈസ് അബൌട്ട് എക്സ്റേ ഡിഫ്രാക്ഷൻ. സോ ഫ്രം ദിസ് വി ക്യാൻ സ്റ്റഡി ദ ക്രിസ്റ്റൽ സ്ട്രക്ചർ. അതിന് ഡൗട്ട് ഉണ്ടോ? Any doubt? X-ray diffraction. ആർക്കില്ല? എടുത്തോ?
എടുത്തു സാർ.
Okay.
Yes, sir.